Hello students, welcome to this lecture 1 circles. So in this chapter we will study number of tangents from a point on a circle, and then we'll study summary of this chapter. Okay, so let us start. So to get an idea of the number of tangents from a point on a circle, let us perform the following activity. So by performing the following activity, will get an idea of the number of tangents from a point on a circle. Okay. So let us perform the following activity. So activity 3. So by this activity, we will we will get an idea of the number of tangents from a point on a circle. So first of all, we have to draw a circle on a paper. Okay. So then take a point P inside it. And can you draw a tangent to the circle through this point? Okay, so this is our question. Can you draw a tangent to the circle through this point? So if we take the point inside the circle, then you will find that all the lines through this point intersects the circle in 2 points. Okay, so in this case, you will get all the lines that is passing through the point P at the second of this circle. Okay, so it is not possible to draw any tangent to the circle through a point inside it. Okay, so if you see this figure, so in this figure here we basically take the point P. Okay, and we draw some lines, and these lines are intersecting the circle at 2 points. Okay, and for this figure, for this if we take P point inside the circle, then basically we will not get a tangent to a circle. Okay, so through this point intersect through this, if we will find all the lines through this point intersect the circle at 2 distinct points, so it is not possible to draw any tangent to a circle through a point inside it. Okay, so now second, if we take the point which touch the circle at point P. Okay, so next take a point on the circle and draw tangents through this point. So you have already observed that there is only one tangent to the circle at such a point. So we have studied in your previous lecture. There we have proved a theorem. Okay, by that theorem we get this concept, this idea. There we observe that there is only one tangent to the circle at such a point. Okay, so in this case, if we take a point P on the circle, then we actually get only one tangent to the circle. Okay, and now if we now take the point P outside that circle, here we do not take the point inside the circle and on the circle. Here we basically take the point P outside the circle. Okay, so now let us see what will happen. So if we finally take a point P outside the circle and try to draw tangents to the circle from this point. So what do you observe? So if we take our point P outside the circle, then what do you observe here? So what do you observe? So you will find that you can draw exactly 2 tangents to the circle, this point. Okay, so then the point of contact are basically T1 and T2. So at point T1 and T2, these 2 lines intersect the circle at intersects. Okay, so these 2 tangents will get if we take the point P outside the circle. Okay, so here we get 3 cases. Okay, so in first case, if we take the point P inside the circle, and in this case we will get those lines which will intersect the circle at 2 points, and therefore it is not possible to get a tangent to the circle. Okay, and in second case, there we have seen if we take the point P on the circle, then in this case if we draw a line at this point, then we'll get exactly one tangent to the circle. Okay, and in third case, if we take P point outside the circle, then that case we can draw two tangents to the circle. Okay, so that we have observed from this activity. Okay, so we can summarize this fact as follows. Case 1, there is no tangent to a circle passing through a point lying on the circle. Okay, and in case 2, there is one and only one tangent to a circle passing through a point lying on the circle. Okay, and in case 3, there are exactly two tangents to a circle through a point lying outside the circle. Okay, so now in figure 10.6 of 3, T1 and T2 are the points of contact of the tangents PT1 and PT2 respectively. Okay, so at T1 and T2, there actually we have common points with tangents PT1 and P2 with the circle. Okay, so that is why T1 and T2 are the points of contact of the tangents PT1 and PT2. And the length of the segment of the tangent from the external point P and the point of contact with the circle is called the length of the tangent from the point P to the circle. Okay, so here we have studied length of the tangent. Okay, so what is length of the tangent? So the length of the tangent of the length of the segment of the tangent from the external point P and the point of contact T1 and T2 with the circle is called the length of the tangent from the point P to the circle. Okay, so now note it down that in figure 10.6 of 3, PT1 and PT2 are the length of the tangent from P to the circle. Okay, so T1, T2 are the point of context of the tangents PT1 and PT2 respectively, and PT1 and PT2, they are actually length of the tangents from point P to the circle. Okay, and the length PT1 and PT2 have a common property. Can you find this property? So they have a common property, and that property we will discuss here. So measure PT1 and PT2, are these equal? And in fact this is always so. Okay, so let us give a proof of this fact in the following theorem. So here we'll take the following theorem, and by proving that theorem, here we'll answer these two questions. Okay, so can you find this and measure PT1 and P2, are these equal? That will prove by this theorem. Okay, so let us see the theorem 10.2. So student, here the length of the tangents drawn from an external point to a circle are always equal. Okay, so PT1 and PT2 in our figure 10.3, these two the length of the tangents are basically equal. Okay, so the length of the tangents drawn from an external point to a circle are always equal. So let us prove it. So we are given a circle with center O, a point P lying outside the circle, and two tangents PQ and PR on the circle from point P. That is shown in figure 10.7. Okay, so you can see figure 10.7. There we are given a circle with center O and a point P lying outside the circle. Okay, and two tangents PQ and PR on the circle from the point P. And we are required to prove that length of the tangents PQ and PR are equal. Okay, so we are required to prove that PQ is equal to PR. Okay, so we have to prove it. So let us prove it. So here you can see this figure 10.7. Here we take this circle with center O and radius OQ and OR. And here the length of the tangents are PQ and PR. And here we have to prove that PQ is equal to PR. So from this we join OP, OQ and OQ and OR. Okay, so we join OP, OQ and OR. Then angle OQP and angle ORP, they are right angles. Since we have proved in our previous lecture this theorem, the radius of the circle, this is perpendicular to the tangent to the circle at that point. Okay, so radius of the circle at that point, and this is perpendicular to the tangent to the circle at that point. Okay, so here OQ is perpendicular to the PQ, so this angle OQP is 90 degree, and this is also this is also applicable. So OR, this is also perpendicular to PR, so ORQ, this angle are right angle. So because these are angles between the radii and tangents, and according to the theorem 10.1, they are right angles. Okay, so now in right triangles OQP, so this is our right triangles. Why? Because this angle is 90 degree, so this angle is basically right angle triangle. Okay, so from this right angle triangle OQP and ORP, here OQ is equal to 1. Why they are equal? Because they are actually same radius of the circle. Okay, so the radii of this same circle. And here OP is equal to OP because they are common in both. Okay, so OP is equal to OP and OQ is equal to OR because they are radii of the same circle. Okay, so therefore we can say triangle OQP, this is congruent to triangle ORP. Okay, so you have studied in your class 9th about congruency of two triangles. So here by these two sides are equal and one angle is equal, that is we can use side angle side criteria for congruency. Okay, so we can say therefore triangle OQP is congruent to triangle ORP. Okay, and this gives us PQ is equal to PR. Okay, so PQ is equal to PR because they are congruent angles. Okay, so this is why this gives us PQ is equal to PR. Okay, so here we proved we proved the required this PQ is equal to PR. That means the length of the tangents drawn from an external point to a circle are equal. Okay, so the length of the tangents drawn from an external point to a circle are equal. And here we will give some remarks. So in number 1, the theorem can also be proved by using the Pythagoras theorem. Okay, as follows. If we take triangle PQ, this triangle, if you take this triangle OQP, and from this triangle you can say PQ square is equal to OP square minus OQ square, and this is equal to OP square minus OR square, and this is equal to PR square. And as OQ is equal to OR, which gives us PQ is equal to PR. Okay, so by using Pythagoras theorem, here we can easily prove this theorem. Okay, we can prove this theorem by using Pythagoras theorem. And second remark, note it down also that angle OPQ is equal to angle OPR. Okay, so therefore OP is the angle bisector of angle OPR. Okay, so OP is basically the angle bisector of angle QPR. That is, the center lies on the bisector of the angle between the two tangents. Okay, so note it down, this remarks is very important. Okay, and this remark is also very important remark. This is shortcut proof of the above theorem. Okay, so this will help you to solve some examples. Okay, so here we'll basically take some examples. So let us explore some examples. Okay, so in example 1, here we have to prove that in two concentric circles, the chord of the larger circle which touches the smaller circle is bisected at the point of contact. Okay, so we have to prove that in two concentric circles, means concentric means they are the two circles center same. Okay, they have same center. Okay, so two circles, they have same centers, that are called concentric circles. So the chord of the longer circle with which touches the smaller circle is bisected at the point of contact. Okay, so let us prove it. So here you can see this figure 10.8. so here this circle and this circle, they are actually concentric circle. They have common center O. Okay, so we are given two concentric circles C1 and C2 with center O, and a chord AP of the larger circle C1 which touches the smaller circle C2 at the point P. You can see this figure 10.8. So we need to prove that AP is equal to BP. Okay, we need to prove that AP is equal to BP. So basically we are given two concentric circle with center O and a chord AB. Okay, and this is actually chord of the larger circle C1 which touches the smaller circle C2 at the point P, and here we have to prove that AP is equal to BP. AP is equal to BP. So let us join OP. Then AB is a tangent to circle C2. Okay, at point P, and OP is its radius. Okay, so therefore by theorem 10.1, OP is perpendicular to AB. Okay, so OP is perpendicular to AB. So now AB is a chord of the circle C1 and OP is perpendicular to AB. So therefore OP is the bisector of the chord AB. Okay, as the perpendicular from the center bisects the chord. Okay, that is AP is equal to BP. Okay, I think I hope this is clear to you. So here basically AB is a chord of the circle C1 that we have taken, and here OP is perpendicular AB since by the theorem of 10.1. Okay, so therefore OP is actually bisector of the chord AB. Okay, so as the perpendicular from the centers bisect the chord. Okay, so that is AP is equal to BP, and hence proved. And now let us see example 2. So here in this example, here we have two tangents TP and TQ that are drawn to a circle with center O from an external point T, and here we have to prove that angle PTQ is equal to 2 times angle OPQ. Okay, so we are given a circle with center O, an external point T. Okay, and two tangents TP and TQ to the circle, where P, Q are the points of contact, and we need to prove that angle PTQ, this angle is equal to 2 times angle OPQ. Okay, so this angle is equal to 2 times this angle. Okay, that we have to prove here. So basically we have taken this circle with center O and external point T, and we have drawn two tangents on this circle, and the point of contacts are P and Q respectively, and here we have to prove that angle PTQ, this is equal to 2 times angle OPQ. Okay, so let here angle PTQ is equal to theta, and now by theorem 10.2, TP is equal to TQ since they are length of the tangents of the circle. Okay, with center O. So TP is equal to TQ. So TPQ is an isosceles triangle. Okay, so for isosceles triangle we can say therefore angle TPQ is equal to angle TQP, and that is equal to half of 180 degree minus theta. Okay, and this is equal to 90 degree minus 1/2 theta. Okay, So angle TPQ is equal to 90 degree minus 1 by 2 theta. So now also by theorem 10.1, angle OPT, this is equal to 90 degree. Okay, so angle OPQ, this is equal to angle OPT minus angle TPQ, and this is equal to 90 degree minus 90 degree minus half of theta, and this is equal to half of theta, and this is equal to 1 by 2 angle PTQ. Okay, so since angle PTQ is equal to theta, so this is equal to 1 by 2 angle PTQ, and this gives us angle PTQ. This is equal to 2 times of angle OPQ. Okay, so angle PTQ, this is equal to 2 times of angle OPQ. Now let us see example 3. So here we have PQ is a chord of the length 8 cm of a circle of radius 5 cm, and the tangents at point P and Q intersect at a point T that you can see in figure 10.10. Here we have to find the length TP. Okay, so PQ, this is a chord of the length 8 cm of the circle with center O. Okay, and radius 5 cm of the circle, and here the tangents meets at point P and Q respectively. Okay, at a point from a point T. So here we have to find the length of TP. Okay, so let us solve it. So join OT. So in this picture we join OT. Okay, so if we join OT, then let it intersect PQ at the point R, and then triangle TPQ is isosceles and TO is the angle bisector of angle PTQ. So OT is perpendicular to PQ. Okay, and therefore OT bisects PQ, which gives PR is equal to RQ is equal to 4 cm. Okay, so PR is equal to RQ. PR is equal to RQ is equal to 4 cm. So now also OR, this is equal to square root of OP square minus PR square by Pythagoras theorem. Okay, so OR is equal to square root of OP square minus PR square, and this is equal to square root of 5 square minus 4 square centimeter, that is equal to 3 cm. Okay, so angle TPR plus angle RPO, this is equal to 90 degree, and this is equal to angle TPR plus angle PTR. Why? You can observe the figure, then you will easily say this angle plus this angle is 90 degree, and this angle plus this angle is equal to 90 degree. Okay, so here from this equation, angle RPO, this is equal to angle PTR. Okay, so therefore right triangle TRP is similar to the right triangle PRO by angle similarity criteria. So this gives TP by PO is equal to RP by RO, and that is TP by 5 is equal to R by 5, and where TP is equal to 20 by 3 centimeter. Okay, so TP is equal to 20 by 3 centimeter. And here note it down, TP can also be found by using Pythagoras theorem. So as follows, we can let TP is equal to X and TR is equal to Y, and then by Pythagoras theorem taking right triangle PRT. So here x square is equal to y square plus 16, and taking right triangle OPT, here x square plus 5 square is equal to y plus 3 whole square. Okay, so now subtracting equation 1 from 2, then we get therefore 25 is equal to 6y minus 7, or y is equal to 32 by 6, and that is equal to 16 by 3. Okay, and x square, this is equal to 16 by 3 whole square plus 16, that is equal to 16 by 9 times 16 plus 9, and this is equal to 16 times 25 by 9, and this implies x is equal to 20 by 3. Okay, so x is equal to 20 by 3 centimeter. And now here we'll summarize what we have studied in this chapter. So in this chapter, basically we have studied the meaning of the tangent to a circle. Okay, so tangent to a circle is nothing but a line which intersects to the circle at exactly one point. Okay, and the tangent to a circle is perpendicular to the radius through the point of contact. Okay, that you have proved in our previous lecture, that you have studied in our previous lecture. Okay, so the tangent to a circle is perpendicular to the radius through the point of contact. And third, the length of the two tangents from an external point to a circle are equal. Okay, so these things we have studied in this chapter, and if you have any doubt or query, then you can ask your doubt in our website doubt section. Okay, so you can visit our website doubt section. So, and if you want to attempt subject wise mock test, then you can register yourself in this website. Okay, jetest.porter.ai. And if you have if you have any doubt, then you can ask any doubt regarding this video lecture or any subject doubt like mathematics, physics, chemistry, biology. Okay, then you can freely ask on this website sathee-ENGG. Okay, and if you have any doubt, so how to join mock test, or how to ask Sathi QR code, how to ask subject doubt, then you can visit our these videos, how to videos. Okay, and you can also visit our this website sathi.footer.ai. There you will get many contents that will help you in your preparation. Okay, so I stop here this lecture. Thank you very much to all of you.